Hello everyone, this is chapter 9 on optimization, a special variety of equilibrium analysis. The reference book is AC Chiang. Let's start with this chapter. Now first and foremost we need to understand what do we mean by the term optimization. Optimization means the quest for the best, that is maximizing or minimizing a given objective function given some conditions which are being laid down. For example, we wish to maximize firm's profit, we wish to maximize consumers' utility, or if we wish to minimize the cost of the producer. So these are known as the objective function, basically which represents what the decision maker wants to optimize. So the goal for the firm is to maximize profit, the goal of the consumer is to maximize utility, the goal of the producer is to minimize cost. So the objective function is going to convert this goal into a formula. Let's understand this with few examples. The first is profit maximization. The goal is to maximize profit. We denote profit in mathematics by this symbol pi, which is the formula for profit maximization is the revenue minus the cost, which is denoted in terms of the quantities produced by the producer. So variables which are under the control of the decision maker, like the output level of the firm or the amount of goods purchased by a consumer, these are the decision variables. So over here in the first example, the decision variable is the output which is in the hands of the producer. The next example, utility maximization. The goal is to maximize the utility. So utility function denoted by U, which is a function of two quantities of goods consumed by the consumer, which is denoted by X and Y. Third example, cost minimization. The goal is to minimize the production cost. The objective function is cost C, denoted by C, which is a function of labor and capital. So the decision variables which are under the control of the decision maker, like the output level or the amount of goods purchased by the consumer in case of utility, or the labor and capital in case of the cost minimization. So what do we do with this objective functions in optimization? These are the three crucial steps that we usually take into account. The first is we write the objective function. The second is that we take the derivatives with respect to the decision variables, like with respect to output level of a firm in case of profit maximization or so, and then we use some conditions which are being there to find the maximum and the minimum values. So these are the few important steps that needs to be done in the entire chapter in finding the maximum minimum values. Now let's look at another topic before we go on to do some examples. Let's understand what do we mean by relative and absolute extremum. This is this explains, this section 9.2 explains the distinction between relative and absolute extremum, and this should be clear with each one of you. The first, let's understand the relative or the local extremum, which is the highest or the lowest value compared to nearby points. So like for example in this example, if you look up in this there are three figures that are being there. Let's label this as figure 1, figure 2 and figure 3. So if you look up at figure 3, points E and F, as you can see, they represents our relative extremum points. Because it lies the maximum value and the minimum values lie in the immediate neighborhood of the points only. So these are known as the relative extremum points or the local extremum points. The next distinction is in case of the absolute extremum, which is this absolute extremum, or which is also known as the global extremum, which means the highest or the lowest value over the entire domain. Like in second figure, as you can see, point D, this point D represents the absolute minimum point because it lies over the entire domain. Then in the first figure, as you can see, points A, B and C, they are neither maximum nor minimum, as all the values of x result in the same value of y. So nothing can be said about it. So this is what do we mean by relative and absolute extremum point. The distinction is clearly written over here and you can see it. Now let's look up at the first derivative test. Let the function be fx and the first derivative is denoted as f dash x. We denote first derivative test as f dash x, which plays a very important role in search for extreme values. Again, before coming up to the conditions, we are assuming that y is equal to fx is a continuous function and it possesses a continuous derivative. Let's look up at the conditions for finding the extreme values. If f dash x, the first derivative, changes its sign from positive to negative from the left of that point, let that point be x is equal to x naught, to the right of x naught, then that point is known as relative maximum point. As you can see in this figure, relative maximum point at x equal to x naught, it is changing its value from positive to negative, from left of x naught to right of x naught. So this is a relative maximum point at x equal to x naught. If f dash x changes its sign from negative to positive, that is your relative minimum point, as in this figure 2. As you can see, pehle negative niche ja raha hai and then it is a positive sign indicating a relative minimum. If now this will also come up in your mind that if it doesn't change its sign from either from the left to the right, then what is it? The last case, then it is neither maximum nor minimum value, and that point is known as an inflection point. So if it doesn't change its sign, it is neither maximum nor minimum. This point is known as inflection point. To understand it better, let's look at first example where we have to find the relative extrema points using the first derivative test. So if let's say this is the example, y is equal to fx is equal to x cube minus 12x square plus 36x plus 8. How do we do it? We are going to first find the first derivative test to get the critical values. So f dash x is equal to 3x square minus 24x plus 36 to get the critical values, that is the values of x, which is going to satisfy the condition f dash x equal to 0. We are going to set this quadratic equation function equal to 0 and get the quadratic equation. So this is 3x square minus 24x plus 36 equal to 0. So either by applying the quadratic formula or by factoring the polynomial, we can find the its solutions or the roots which are going to be there. So this is x square minus 8x plus 12 equal to 0. So this will give us x minus 6 and x minus 2 equal to 0. So the two critical pair of roots or the solutions that we are getting is x is equal to 6 and x is equal to 2. Now what do we do? Let's look up at x is equal to 2. At x equal to 2, we are going to look up at the points x less than 2. What is the value of our f dash x going to be? F dash x was 3x square minus 24x plus 36. So even if we put, let's say, any value, we put in value x equal to 1. So we are getting, if we put x equal to 1 into f dash x, we will be getting 3 minus 24 plus 36. That means f dash x is coming out to be greater than 0. At x less than the value of 2, our f dash x is coming out to be greater than 0. For x values to the right of 2, let's look up x values greater than 2, we are getting f dash x. We can put any value greater than 2. So let's say that we have put 3 or 4 instead of x. So if we put 3, so this is 3, 3, 9, 9, 3, 27 minus 24 into 3 plus 36. So we are getting f dash x less than 0. So in the immediate neighborhood of x is equal to 2, this is the condition which is being fulfilling at x is equal to 2. So now what can we say? If the sign is changing from positive to negative, it means, see, if it is changing from positive to negative, from left of x naught to right of x naught, it is a relative maximum point. So this indicates a relative maximum at x equal to 2. We can also find the value at f equal to 2 if we put it in the function back. The function is x cube minus 12x square plus 36x plus 8. So if we put in the value x is equal to 2 in our function, we are going to get 40. So the at x equal to 2, the corresponding value of the function is 40, which is a relative maximum point. Now another point, let's look up at x equal to 6, our second critical point, which is f dash x is equal to 3x square minus 24x plus 36. So at x less than 6, let's look up f dash x. If we put up any value 4, 3, 4 or 5, we know that we are getting a f dash x is coming out to be less than 0. And if we take x value greater than 6, then f dash x is coming out to be greater than 0. Now if the sign changes from negative to positive, this indicates a relative minimum point. So this is relative minimum. So at x is equal to 6, we are getting a relative minimum point. And let's look up at what is the value of the function at f at the value of x is equal to 6. this is will come out to be 8. So and if even if you can also plot the graph correspondingly and look, if we wish to make a graph of this, let's take 10, 20. So at x is equal to 6, the value of the function, the minimum value is 8. And at x is equal to 2, the value of the function is 40, which represents a maximum value. So the value of the function, the graph is going to look like somewhat like this. Where this is the maximum point at x is equal to 2, and the point, let's denote it as A, and this is point B, which is denoting relative minimum at x is equal to 6. So this is how we look up using the first derivative test, we come up with the relative extremum points. The next part of this chapter from 9.3 we are going to look up in our next video.